There we go. All right. So now for this area that's shown, we're asked to find the first moments. Now the first moments are also referred to as the those integrals which we were, so this integral here, right? So this, whoops. So that is basically what the first moment is. And we also want to find the location of the centroid. All right, so the way to going about solving this problem is that you want to divide the area into a triangle, a rectangle, and a semicircle, right? So basically what you're going to do is, and then you find out the centroid of each of those, and then you use you just use the principle of superposition to find out the overall thing, right? So let's go about it, right? So the way to think about it is that if I take this guy, right? So come on, where's my arrow? There we go. So there we go. So now let's look at this, right? So when you're looking at it this way, you can see that the composite area, and remember, always keep your x and y axis the same. That's what you need to do when you're looking at everything together. So looking at the x and y axis, if I just draw it out, so let's draw out a rectangle first. And again, multiple ways to skin a goat. This is just the way that I am doing it, right? So this is like that over there. So you have y and x, right? And for the location of this centroid, what will, this rectangle, what will that, the location of the height be?
80 millimeters.
I hope you said 40, because that's what it is, right? And then the width
yes.
here is 120, right? So that's divided by half. So that will be 60. Right? So 60 millimeters there. Plus, right, what's the next shape? Let's look at this little triangular shape at the bottom over here, right? So this triangular shape like that, right? Again, remember, your coordinate frame has to remain the same, right? So now for the location of the centroid, right, I go to my regular shapes document and I see that for a rectangle, right, from one of the bases, the height of the centroid is equal to h over 3, right? So here it's going to be 120 over 3. And again, guys, we're buzzing through this. If you have any questions, let me know. So this is going to be equal to 120 divided by 3, so 40 millimeters. And you do the exact same thing for this dimension as well, right? So 60 divided by 3, which is equal to 20 millimeters, right? But just to make our lives easy and, to not complicate things too much, just write it in terms of your coordinate frame, right? So just write it as the coordinate system, right? So this distance here, because it's below the x-axis, you can just write it as being minus 20 millimeters. All right, next, I'm going to run out of space. Let's just quickly make some more space. right. Hopefully that's enough. All right, next, let's look at this semicircle on top over here, right? So looking at this semicircle. So we're taking the whole semicircle, right? So for this guy over here, that's my coordinate system, X, Y, like that, right? Let's get the easy stuff out of the way. The radius. So what's the radius of this semicircle?
60.
60, right? It's just going to be 120 divided by 2. So 60 millimeters. What is the distance of the base of the semicircle from the x-axis?
60.
No, 80. It's 80. Right? Semicircle right there. It's 80. Cool. And then for this dimension is going to be equal to 60, right? So where the center of the guy is. Terrible drawing, guys, but this is the center, all right? Then to find the centroid, you have to go up from the center, right? A certain distance, and that's where the centroid is, right? So next question is, what is that dimension? Sweat not. We go to our regular shape, look at the semicircle, and you're told that that height is equal to 4r over 3 pi. So for our case, that dimension is equal to 4r1 over 3 pi, which if we do the math for 60 millimeters, someone check this real quick and tell me if it's wrong. I got 25.46 millimeters. All right, and last not least, we have to take that full circle out of the picture. So we added these two, but superposition says we can also subtract. So minus, right? Same coordinate system. X, Y. Now I'm going to try to do this best I can. There's the center. Right, center's right there. Terrible, terrible. That looks circular enough, right? We'll go with it. So what's the height there? That's 80. Right, and what's the distance there? That's just 120 over 2, which is equal to 60 millimeters. And what am I missing? I think I'm missing something. The radius. We need the radius. So the radius, let's call this one R2, is just equal to 40 millimeters. Problem says it. 40 millimeters. Right? Okay. So those of you who were with me in the statics and strength of materials lab, when we did the centroids laboratory, we made our table, right? So we do the same thing, and I'm sure you guys made this table when you did composites as well. So basically you have your component, you have your area of the component in millimeters squared, right? Then you have the location of that component's X centroid, right? Then you have the location of that centroid's Y coordinate, and then you have your first moments, right? Which is just the A times X prime and A times Y prime, right? So X, sorry, not prime, bar, X bar times A millimeter cubed, and Y bar times A millimeter cubed, right? So there we go. All right, so we have our components, which is the rectangle. Then we have the triangle. my favorite shape. And we have a semicircle. And then we have the full circle. I guess like life, the last thing that we look at, life comes a full circle. All right, I'll stop with my bad jokes today. Okay, so rectangle area. What do we have? We have the area's rectangle is just 120 times 80, right? So we have 120 times 80, which is equal to 9.6. Well, can you guys find this out? I'm not sure if this is right or not.
Yeah, like 9,600.
Yeah, so let's say 9.6 times 10 to the power 3. All right, triangle is what? Half times base times height. The base is 60, height is 120, right? So it's going to be half times 120 times 60, right? Keeping everything in millimeters because we're finding the units are in millimeters squared. What does this guy come out to be equal to?
3.6 times 10 to the 3.
Thank you. 3.6 times 10 to 3. Semicircle. What is the area of a semicircle? Half times pi r squared, right? So the radius of this guy is 60. So half times pi times 60 squared, which is equal to how much?
.6 times 10 to the 3.
5.6 times 10 to the 3. All right, and then we have the circle. But remember, for the circle, because we're subtracting it out, important to have that minus sign outside, right? So half times pi r squared. Over there. Let me draw this in another so that you guys can see the importance of that. All right, there we go. Minus pi r squared. So that's going to be minus how much?
Negative point or -5 times 10 to the third.
-5 times 10 to the third. All right. X bar we found for all of them, right? So for your rectangle, it's equal to 60. For your triangle, it's equal to 40. For the semicircle, it's equal to 60. Then for this guy, it's equal to 60. You've already taken the minus sign. You don't need to do it again. Otherwise, you'll mess things up, right? Similarly, for the y-ordinate, you get, for the rectangle, it's plus 40. For this triangle, it's minus 20 because you're going below the x-axis, minus 20. Then for this thing here, so it's 80 plus 25.46, which should be 105.46, right? Quick maths, yeah, 105.46. And then you have the circle, the y-ordinate is 80, right? So you get 80 there. All right, now we are doing simple products, right? So you guys can clearly see the benefit of potentially doing something like this in Excel, right? It'll just make life so easy. But yeah, let's just be the gluttons for punishment that engineers are. X bar times A, how much does that give me? 60 times 9.6 times 10 to the third.
576 times 10 to the third.
Thank you. 576 times 10 to the third. What about this guy here? 40 times 3.6 times 10 to the 3.
144 times 10 to the third.
144 times 10 to the third. All right. This one now. 60 times 5.6 times 10 to the 3.
336 times 10 to the third.
336 times 10 to the third. And the last one. What's the last one? 60 times that. Oh, quick math, 300.
300.
Yeah, minus 300. Don't forget the minus sign. Times 10 to the third. All right. Similarly, let's go and do for the y one. So for the rectangle, what's your first moment?
384.
Times 10 to the 3, right? 10 to the third.
Yeah.
All right. What's the triangle? 20 times 2.6. So that's a quick one, right? Minus. So it's a minus sign here. So minus 72 times 10 to the third, right? Then sorry, what am I doing? I'm doing 105.46 times 5.6 times 10 to the third.
596 times 10 to the third.
96 times 10 to the 3. All right, and then the last one, what do I have? I have 80 times minus 5, so that should be minus 400 times 10 to the third. All right, last step. Well, next step. Got to sum everything, right? So what is the total area? 9.6 plus 3.6 is 13. Okay, I'm not doing this. Please tell me.
$13.8 times 10 to the third.
Thank you. Times 10 to the power 3. Next, we need the sum of x bar a, which is how much? So the sum of all of these guys.
$756 times 10 to the negative
756. Thank you. So 756 times 10 to the 3 millimeters cube, right? And then here, what do we get? We get, what is that equal to?
$508 times 10 to the third.
All right, so the symbols that are used to refer to your first moments, we didn't look at that in the lecture, but quickly go through here. So the first moments, basically just that, right? Just these guys over here. The symbols are, does anyone remember? Statics, Q, right? So Qx is equal to 508 times 10 to the third, and then Qy is equal to 756 times 10 to the third. All right, new slide. All
And
right,
that's millimeters cubed. Is that what do we have to, are those the
correct,
units?
absolutely correct. Never forget the units, otherwise we're crashing into Mars. Yes, millimeters cube. All right, next, the important thing that we're interested in, centroids, right? So for your x, you're summing everything, the first moments in the x divided by the area, right? So that was, what did we get? We had 756 times 10 to the 3, whoops, 3 millimeters cubed divided by, what do we get for the area? For the area, we got 13.8. Three millimeters squared, millimeters cubed, right? So what is this equal to?
$54.78 times 10 to the 3.
Nope,
54.78.
that's right. No 10 to the 3,
Oh.
right? 10 to the 3 cancels out. So 54, let's just say 54.8 millimeters, right? Careful with the units. All right, similarly, your y is there. So 13.8 times 10 to the 3 millimeters squared. What was 508? Zero cube cancels and 3 cancels. So y bar is equal to what?
36.8.
Thank you. All right, so quick check, right? So if we draw our shape out, right? So you got the y, x, right? So the centroid is such that it is somewhere there, right? So that x bar is equal to 54.8. That guy is equal to 36.6. That looks right. Looks good. Looks about right. So good stuff. All right. Let's look at the next problem, and I think we'll have to call it a day after that one. So the last problem, which was impending motion, I'll post the solutions right after for you guys. All right. So moment of inertia with the shaded area, with about off the shaded area about the x-axis, right? So we do the same thing. We break it up into composite shapes, right? So let's write this one out just so that we have the method. So we have to compute the moments of inertia of the rectangle and half circle with respect to, so WRT always means with respect to, right? So with respect to the x-axis, right? And you can say, oops, what happened here? What did I do? At the moment of inertia. Can you guys still see the screen and my writing all good? My pen is acting funny. Moment of inertia. Right? Everything's good?
Looks
Yeah, all
good.
good.
Okay. Of the shaded area is obtained by subtracting the moment of inertia of the half circle from the moment of inertia rectangle. Right. Also, to find out the moment of inertia of the half circle, you have to find it out you'll have to use the parallel axis theorem and like that, right? So, all right, let's go ahead and do it. So for the rectangle is pretty straightforward. Not going to draw it out. Let's draw out the semicircle. And again, referencing our master document of moments of inertia and shapes around here, right? So the moment of inertia of a semicircle about basically this axis, right? So that's going to be about that axis over there. Okay. Y, X, and then let's have our semicircle like that, right? We need to know where the location of the centroid is for the parallel axis theorem, right? So let's say that we draw this axis parallel to the x-axis. Let's call it A prime like that, right? This height of the base is just equal to 120 millimeters, right? And then the radius for the semicircle is how much? Is 90 millimeters, right? So the location of the centroid we know is 4r over 3 pi, right? So that is, let's call that dimension A, right? That is equal to 4. Let's say that this is r over 3 pi. So how much does that turn out to be equal to?
$38.2.
Thank you. 38.2 millimeters, right? And then quick maths. From this base, 120 minus that, how much is this dimension equal to?
$51.8.
51.8? No, it should be 81.8, right?
That's what I got. I got 81.8.
There we go. All right. Then let's look at this big rectangle, right? I'm going to draw it out with gray, right? So going to our guy over here, about this x-axis here, it's 1 over 3 b times h cubed, right? So about the x-axis, let's look at rectangle, right? So referencing back our document here, 1 over 3 bh cubed about the x-axis, right? About this edge over here. So Ix is equal to bh cubed over 3, right? So what is B? 240. What is H? 120. So you get 1 over 3 times 240 times 120 cubed. What does that turn out to be equal to? Guys? Where'd everyone go?
Is it
Um,
138 times 10 to the 6?
Sure.
Yeah, I agree.
And what are the units?
Millimeters.
No, millimeter to the 4, right? Millimeters to the power 4. That's right. All right. Next, let's move on to our semicircle color coordination. First things first, area of semicircle. 1 over 2 pi r squared, which is 1 over 2 pi, radius is 90, right? So 90 squared. What does that come out to be equal to?
.7 times 10 to the 3.
Thank you. 12.7 times 10 to the power 3 units. Millimeter squared, right? Come on. You guys have to be quick on that one. All right. Then let's find, we know the moment of inertia about AA prime from our cheat sheet over here, right? So about this x-axis, we know that it's that. So let's say IAA prime is just equal to, what did it say? It said Ix equals 1 over 8 pi r to the power 4. So you get 1 over 8 times pi r to the power 4, right? So what we're doing right now is we know what the moment of inertia about AA prime is. We will use that, use the parallel axis theory in reverse to find out what the moment of inertia about the centroid is, and then use the moment of inertia again to find out what the moment of inertia about the x-axis is, right? Because the parallel axis theorem only works if you know the moment of inertia about the centroid, right? So this is what we're doing first. We're finding the moment of inertia about the centroid using the parallel axis theorem in reverse, right? So 1 over 8 times pi times 90 to the power 4. And how much does that come out to be equal to?
2.58 times 10 to the 7th millimeters to the 4th.
Thank you. 2.58 times 10 to the 7 millimeters to the power 4, right? Next, moment of inertia about centroid. So let's continue with the thing that we've been using, right? So we call that x prime, right? Moment of inertia so then now you have to use the parallel axis theorem in reverse, right? Because IAA prime is going to equal IX prime plus A times this distance little a squared, right? So what that means is that IX prime is equal to IAA prime minus A times little a squared, right? So IX prime is equal to, what did we find? We found it to be 2.58 times 10 to the 7 minus, what was our area? Our area was 12.7 times 10 to the 3 times little a squared, and little a is equal to 38.2, right? Times 38, whoops, 38.2 squared. Right, everything's in millimeters, so we're good. So what does this come out to be equal to?
.538 times 10 to the 7.
I don't have that.
I didn't square my 38.2.
There you go.
Would it be 7.26 times 10 to the 6th?
Yes. So
Millimeters to the fourth.
7.26 times 10 to the 6th millimeters to the power 4, right? And now we're good to do what we need to do about the x-axis, right? So let's see, in your page. So Ix is equal to my moment of inertia about my centroid, right? About the x prime plus, now what is the addition going to be? It's going to be the area times b squared, right? Little b squared. Whoops. That's equal to Ix prime we found was 7.26, right? Without looking over at the other slide, times 10 to the 6th plus area is 12.72 times 10 to the 3 times, what was B? 81.8, right? So 81.8 squared, right? So what does this come out to be equal to?
.24 times 10 to the 7.
4 times 10 to the 7 units.
Millimeters to the 4th.
Meters to the 4th, right? So now we know that the Ix of my composite is going to be my Ix of the rectangle minus Ix of the semicircle, right? Simple subtraction. So where was I? For the rectangle, it was 138 times 10 to the 6th. How much is that?
.56 times 10 to the 7.
Can someone confirm that real quick? Because I don't have the final answer with me.
I got the same thing.
That's what I got.
Units?
Millimeters to the 4th.
Millimeters to the 4th. All right. There you go. That's your answer. Good stuff. All right, guys. Homework 1 has been posted under the assignment section in Brightspace. It's due a week from now. It's basically a quick review of static. So these are easy points for you guys. So make sure you go ahead and do that. We will have the first tutorial session hosted by the LA tomorrow. So if you want to take use of that opportunity, come to class tomorrow. We're still figuring out the time. It's either going to be at noon or 5 p.m. I will let you guys know in an email later today when it's going to be, and also we'll share Zoom details with you, so that you can log on then. All right.
That'll also be recorded.
That will also be recorded. Yeah.
Okay,
Well,
cool.
yeah, sure. Let's record it. Well, typically it's a Q&A session, right? So I don't know how useful that is, or maybe like a study session. So I don't know how useful it will be, but let's just record it for an hour. That's a good idea.
Better safe than sorry.
Better safe than sorry. You're absolutely
Yeah, I
right.
like that.
All right, and I'll also post all of the homeworks later this week for the whole semester, so that if you guys want, you can get started on those.
Maybe
Right.
maybe you talked about this in like the first class, but who's the LA for this course?
Dirty Dan, Daniel St. Peter,
Okay. Busy man.
busy man, busy man. All right, thanks guys. See you guys on Thursday.
That was good to see you Thursday.
Thank
Thank
you.
you.